Okay, for what we have regarding the continuation of utilizing V-substitution, okay, we have a Bernoulli equation, which is basically at this stage of the game a revisiting of what we have had with linear first order differential equations, and we have for the Bernoulli equation, okay, here we have the derivative dy over dx plus p of x times y is equal to q of x times y to the n. And if we have that the degree to which y is raised on the right hand side, okay, if we have that n is equal to 0 or 1, we're going to have a first order linear differential equation. Okay, but now if we have other situations, okay, we're going to have V substitution to arise. Okay, we're going to have that V is equal to y raised to the 1 minus n degree. And what we have with the Bernoulli equation, okay, we have the translation, okay, in terms of the variable v. This will become dv over dx plus the quantity of 1 minus n times p of x times v is equal to 1 minus n quantity times q of x. And we will look at a sample of a first order linear differential equation and a case of where we have a nonlinear Bernoulli equation. Okay, so let's say if we have as a case of a linear differential equation where we had to be first order in y, and something that we have encountered pretty much, say we have dy over dx minus 2 over x times y is equal to x. Okay, so you don't have a y term on the right hand side, okay, so this would be like x times 1 or x times y to the 0, so the degree n is equal to 0. So dy over dx minus 2 over x times y is equal to x. That is a first order linear differential equation. And okay, so here we can utilize the integrating factor. So you have p of x is equal to negative 2 over x. And the integrating factor, you're going to have e to the integral of negative 2 over x dx. And that is going to translate to e to the negative 2 times the natural logarithm of x is equal to e to the natural logarithm of x to the negative 2. And that is going to translate out to x to the negative 2 or 1 over x squared. And if we take the integrating factor and multiply what we have in this differential equation, so you can distribute, okay, but here we have 1 over x squared times the left hand side, which has the derivative, is equal to x over x squared, which is going to be 1 over x. And so again, the left-hand side is going to be the product rule expansion of what we have as we take the derivative nx of the product of the integrating factor, which we have with 1 over x squared times the dependent variable y. And again, we have is equal to 1 over x. And again, integrating over both sides. Okay, so left-hand side, okay, we had the differential dx switch over to the right hand side. Left hand side we have 1 over x squared times y, or y over x squared is equal to the integral of the reciprocal of x dx. And here we have y over x squared is equal to the natural logarithm of x followed by the constant. And we have, for the general solution, we have that y is equal to x squared times the quantity of the natural logarithm of x, or the absolute value of x, followed by the constant. Okay, now continuing on with a Bernoulli equation, and I just want to mention something. We have been fresh off of the homogeneous first order differential equations, and I just want to mention something. If I were to express this equation and try to put this in terms of a homogeneous differential equation, so if I were to divide by xy squared, And if I were to try to split up, okay, so if I divide x squared by xy squared, so I would have x over y squared, and for y cubed all over xy squared, so this would be y over x. Okay, now we almost have a homogeneous differential equation, and we would have if x squared over xy squared has simplified to x over y. In other words, like before, whenever we had homogeneous equations where we could apply substitution, well, guess what? X over y squared prevents the reduction to x over y, or the reciprocal of v plus y over x, which reduces to v. So we had the y over x portion, but the excess in the degree to which y is raised in the denominator for the first term, okay, this prevents that equation from becoming homogeneous. Okay, so looking at what we have in terms of doing a second take. All right, so again, we had for the reduction, okay, so you have dy over dx. Again, if we divide by xy squared, so we have x over y squared, and we can say that we have for y over x, by then we can say we have 1 over x times y, and here we're going to have a linear in y expression, and I have a Bernoulli equation, okay, that is going to be nonlinear, okay, and so I can move the first order term in y over. So I can say that I have dy over dx minus 1 over x times y is equal to x over y squared. Okay, and if you notice, okay, we have for the degree in n, okay, at the very end, I'm just going to stress this. So you have like x times y to the negative 2. So the value n is equal to negative 2. And for what we have, just setting the stage, and I'll just rewrite this. All right, so we have that p of x is equal to negative 1 over x, and now we have for q of x, okay, now q of x is going to be equal to the numerator which we have at x and once again we have the n is equal to negative 2. And just setting the stage here, again, we have for v, substitution variable. Okay, so we have that v is equal to y raised to the 1 minus n degree. Well, guess what? We have n at negative 2, so we have 1 minus n is equal to 1 minus negative 2, and that is equal to 3. So in setting the stage that we have here, so we have that v is going to be equal to y to the 1 minus n, and that's going to be to the third power. So I'm just going to rewrite this. So we had the v is equal to y to the third. And putting this equation in terms of y equals, so essentially taking the cubic root of both sides, we're going to have that y is equal to v raised to the 1/3 power. And for this relation, if I take the derivative in x of both sides, okay, so the left-hand side, okay, so we have dy over dx. Okay, and that is going to be equal to, okay, so you have taking the derivative in v. Okay, so you have 1/3 of v to the negative 2/3, and I'm taking the derivative in x of our expression. So we have in the attachment, okay, we have dv over dx. And if you notice, okay, going back to our original equation, okay, so just taking what we have in the rewrite, because you have dy over dx, and you have 1/3 of v to the negative 2/3 dv over dx. And we have minus 1 over x. And we have times y, so that is going to be v to the 1/3. And that's going to be equal to x over y squared. Well, guess what? Y squared would be v to the 2/3, and since I have the reciprocal of this, okay, that is going to be x times v to the negative 2/3. Okay, and if you notice, okay, I want to write the derivative term as only dv over dx. So to go from 1/3 to 1, I'm going to multiply by 3, and from v to the negative 2/3 to v to the 0. So I'm going to multiply this part, or this stage of the equation, by 3 times v to the 2/3. And for what is going to arise here, okay, so 3 times 1/3 is 1, v to the negative 2/3 times v to the 2/3. Okay, that is going to go to 1. So we now have dv over dx, and we have for v to the 2/3 times v to the 1/3, this will be v, and we have 3 times negative 1 over x, so we're going to have minus 3 over x times v to the first, and that is going to be equal to 3 times x and v to the 2/3 minus 2/3. Okay, well, that's just going to be 3x times 1. And if you notice, we have this equation rewritten in terms of the substitution variable v. Okay, now, so we have for the integrating factor in the substitution variable v. Okay, so we'll, instead of p of x, we're just going to refer to this as rho. So you have like rho of x is equal to negative 3 over x. And we have in terms of the integrating factor in the substitution variable. So you have e to the integral of rho of x dx. So that's going to be e to the integral of negative 3 over x dx. So that is going to be e to the negative 3 times the natural logarithm of x. And you have e to the natural logarithm of x to the negative 3. And by then you can say that we're going to have the reciprocal of x cubed for that integrating factor. And so taking what we have in the standard form in the substitution variable v. So if I take what I have here, again, setting the stage, so you have 1 over x cubed times the left-hand side. Again, do not worry about distributing. But for 1 over x cubed times 3x, so that is going to become 3 over x squared. And for what we have on the left-hand side, again, we're going to have, if you were to multiply, okay, we would have the product rule expansion of taking the derivative in x of the integrating factor, again, which we have the reciprocal of x cubed. Again, we have times the dependent variable v. And again, we have is equal to 3 over x squared. And integrating over both sides. Okay, so we have v over x cubed is equal to the integral of 3 over x squared dx. And so we have v over x cubed is going to be equal to the negative of 3 over x followed by the constant. And if I were to isolate v, so if I multiply by x cubed, so we have negative 3 x squared plus cx cubed. Now I'm looking at putting the results in terms of x and y. So I had set the stage having set v equal to y to the third. Again, we had that v was equal to y to the third. And with back substitution, so we have that y to the third is equal to negative 3x squared plus cx cubed. And as far as I'm concerned, you can leave the answer in this particular form. And if you were to isolate y, okay, taking the cubic root of both sides, and we can say that we have y is equal to the quantity of negative 3x squared plus cx cubed all raised to the 1/3 power.